Ever get the feeling that math is kind of like a secret language? Well, in a lot of ways, it totally is. And today, we're going to crack the code that describes the world all around us, from the simplest straight lines to the wildest curves you can imagine. Let's dive right in.
So just think about it for a second. You've got a perfectly straight line. That graceful arc a ball makes when you throw it, that's a parabola. And then you have the insane dips and climbs of a roller coaster. They all seem so different, right? But believe it or not, they are all described by the exact same mathematical idea. Any guesses?
The answer is just one word: polynomials. This is the master key that unlocks how all of these shapes are related. And in this explainer, we're going to see exactly how it all works.
Okay, so first things first, we got to get on the same page about what a polynomial actually is. Let's break down the absolute fundamentals.
Now I know that sounds a little textbooky, but the most important part, the one golden rule you have to remember, is that last bit: non-negative integer exponents. All that means is that the powers of our variables have to be nice, happy whole numbers. You know, like 0, 1, 2, 3, and so on. No fractions, and definitely no negatives.
Let's look at a classic example here. 3x squared minus 5x plus 7. This whole thing is made up of a few parts. Each of those chunks, like the 3x squared, the negative 5x, and the 7, we call a term. And the number out front, like the 3 and the negative 5, that's the coefficient. And of course, x is our variable. See? Pretty simple when you break it down.
All right, Pop, quiz time. What do you think? Take a look at this expression. Is it a polynomial? Just remember that golden rule about the exponents.
And the answer is a big no. Here's the catch. That 1 over x term is actually just a sneaky way of writing x to the power of -1. And since negative exponents are a major no-go, this guy fails the polynomial test.
Okay, let's try one more. How about this one? Is 4x to the 1/2 minus 5 a polynomial? Again, all eyes on that exponent.
Nope, this one's out too. An exponent of 1/2 is really just another way of writing the square root. And since fractions aren't integers, this doesn't make the cut. So the big takeaway here is the exponents have to be clean, whole numbers, period.
So now that we're basically pros at spotting a polynomial, let's talk about how we sort them. You know, just like biologists classify different species, mathematicians have a system for classifying polynomials so we can understand them better.
And the single most important way to classify a polynomial is by its degree. It's super simple. You just find the term with the biggest exponent on the variable. That number, that's the degree. And it tells you a ton about what the polynomial is going to look and act like.
And this idea of degree leads us to some names you've probably heard before. A polynomial with a degree of 1? That's linear. Yep, its graph is just a straight line. Degree 2 is a quadratic, and that gives us that classic U-shaped parabola. And a degree 3 is called a cubic, which makes a more twisty S-shaped curve.
Okay, this next part is where it gets really, really cool. This is the moment where the abstract world of algebra crashes right into the visual world of geometry. We need to talk about zeros. So, a zero of a polynomial is really just two sides of the very same coin. On the algebra side, it's the magic number that you can plug in for x to make the entire expression equal 0. But on the geometry side, and this is the beautiful part, it's simply the exact spot where the graph of that polynomial crosses the horizontal x-axis. They're the same thing.
And a quadratic shows this off perfectly. A parabola can swoop down and cross the x-axis in two different spots. That means it has two real zeros. Or maybe it just dips down to barely kiss the axis at its lowest point. That's one real zero. Or it could just float entirely above or below the axis, never touching it at all. And that means it has 0 real zeros. Now get this, what if I told you that there's a hidden relationship, a secret pattern, connecting the zeros of a polynomial to those coefficients we were looking at earlier? Well, there is, and we're about to uncover it. For any quadratic polynomial out there, if you take its two zeros, let's just call them alpha and beta for now, and you add them up, their sum will always be equal to the negative of that b coefficient divided by the a coefficient. You don't even have to find the zeros to know their sum. It's incredible. And it doesn't stop there. If you take those same two zeros and multiply them, their product will always equal the c coefficient divided by the a coefficient. These two simple formulas are like a massive shortcut. They're unbelievably powerful.
So we've defined them, we've sorted them, we've found their secret relationships. Now it's time for the grand finale. Let's use everything we've learned to build a polynomial completely from scratch, using nothing but its zeros.
And here it is. I call it the polynomial construction kit. This one formula lets you build a quadratic polynomial as long as you know the sum and the product of its zeros. You literally just plug those two numbers right into the template.
Let's walk through one right now. Let's say we want a polynomial that has the zeros 2 and -3. Okay, step 1, find their sum. 2 plus -3 is -1. Easy. Step 2, find their product. 2 times -3 is -6. Now we just substitute those values into our formula. X squared minus -1x plus -6. A little cleanup, and boom! X squared plus x minus 6. We just built a polynomial out of thin air.
So let's just recap. We've seen that the very DNA of a polynomial, its coefficients, can actually predict the sum and product of its solutions before we even find them. And that just leads to one final big question. If a secret that powerful is hiding in plain sight, what other incredible patterns and deeper truths are still waiting to be discovered inside these amazing mathematical objects?